start with the topic vector algebra, we will first recall that what is a vector. Vector is a physical quantity that has magnitude and also some direction. For example, we have a force that we apply in a particular direction on an object and the object is displaced from one point to other at some distance or displacement. It is represented by bold F or an arrow on F or bar on F. Any vector can be represented in this way. And when we talk about vectors, we also talk about scalars. Now we will see what is a scalar. Scalar is a physical quantity that has magnitude but no direction. For example, temperature has no direction but it can be measured. Length has no direction but it can be measured. And the vectors are represented by simply their symbols, no bold or no arrow on their letter or no bar on the letter. So now we have the first subtopic, vector operations. In vector operations we have vector addition and vector multiplication. In vector addition we will see that it is commutative. We apply head to tail rule in vector addition. The head of first vector is joined by the tail of last vector and the tail of resultant vector is joined by the tail of first vector and its head is joined by the head of last vector. This can also be reversed just by changing the position of second vector. B comes before A and this will be the resultant vector. Now if we have A minus B, it does not mean that we are subtracting these vectors. It simply means that B has negative direction or opposite direction. Just the direction of B vector is reversed and this is the resultant vector. Now we will see that vector addition is also associative. That means that we can first add two vectors A plus B and then add C vector in this resultant vector, and we can also add two vectors B plus C and then we add A in this resultant vector. In the figure we will see we will add A vector in B and this will be the resultant vector, and then we will add this resultant vector with this C vector and this will be the final resultant vector. And secondly, on the right hand side we can see we will add this B vector with this C vector and this will be the resultant vector R, and this resultant vector R will be added with A and this will be the final resultant vector. We can see that final resultant vector of both cases is same. Now we will see vector multiplication. Vector multiplication includes scalar multiplication, dot product and cross product of the vectors. Firstly, we will see scalar multiplication. We can multiply a scalar in the sum of two vectors, and we can also multiply a scalar in the vectors separately and then add up or sum up the two vectors. We can see this is a distributive law. Now we will see in the figure, we will take a vector A and multiply it with 2. The magnitude will become twice, and we will consider another vector B and it will become 2B when we multiply it by 2. Now we will add these two vectors 2A and 2B. This will be the resultant vector. On the left hand side we will have this case A and B and this is A plus B sum. Now we will multiply this sum or resultant vector with 2 and its magnitude will become twice. Now you can see that the magnitude of both resultant vectors is same. Now we will see dot product in the vector operations. What is dot product? It is defined by A dot B equals to AB cos theta. And Here theta is the angle between the vectors when they are placed from tail to tail, as we can see in the figure. And the result or answer of this dot product A dot B is scalar, so hence we can name it as scalar product. Now we will see from where cos theta comes. This is the vector B and this is vector A. We will take the components of this vector. This will be the vertical component of A sin theta, and this will be the horizontal component of A cos theta. So this is this A dot B will become AB cos theta. This is A cos theta with B. Now we can see that B dot A is geometrically the product of B times the projection of A along B. It means that if we have B vector in the base and A this way, we will have the components of A sin theta and A cos theta. Now this component of A along B, we will take the product. So this can also be seen as this A dot B. The first vector will come in the base and the second will come as component form. Now we will see that this is commutative. This dot product is commutative. A dot B equals to B dot A. Now in the second figure we can see that dot product is also distributive, which means that we can take dot product of A with the sum of two vectors, and we can also take the dot product of A with separately two vectors. This is the sum of B and C vectors, and we will take dot product of this sum B plus C with this vector A. Now we will see that if we have two vectors parallel, then A dot B will be equal to AB, because cos 0 equals to 1. So if we have a vector A and we take its dot product with itself, its magnitude will be A square. Now we will see that we have two vectors A and B and they are perpendicular to each other. So their magnitude will be 0, because cos 0 is equal to cos 90 equals to 0. Now we will discuss cross product, which is defined by A cross B, which is equal to AB sin theta n cap. This result or answer is always a vector and will definitely have a direction n cap, and this n cap is perpendicular to the plane of AB, as we can see in the figure. This is B vector and this is A, and we have this n vector, unit vector along the y-axis. Now we will see that geometrically A cross B is the area of parallelogram. Basically it is the magnitude of A cross B. Now as we know that the result or answer of A cross B is a vector, therefore we will call it vector product. If two vectors are parallel, the cross product is 0, because sin 0 equals to 0. Now the cross product is distributive. That means we can take cross product of A with the sum of B plus C, and we can also take the cross product of A with B and C separately and then sum up the products. It is not commutative, which means that A cross B is not equals to B cross A. In fact, B cross A equals to minus A cross B. How? B cross A will be written as this form, and when we change the position of rows, we add negative sign with the matrix. Next we have the subtopic component form of vector. For this we will set up Cartesian coordinates x, y, z, and there will be unit vectors I, j, k or x, y, z like shown in the figure, and we will have an arbitrary vector A in this form, and it will have three components ax, ay and az. It will be written as A equals to ax x cap plus ay y cap plus az z cap. These are the components of the vector. Now we will see that the sum, if we want to add two vectors A and B, we will add like vectors or like components. As we can see here, ax and bx have same direction, so they are added separately, and ay and by are added separately, and az and bz are added separately because they have same directions. This is rule number 1 for addition. Now we will see scalar multiplication with the vector A. We will multiply the scalar with all the three components of vector. This is rule number 2. Now for rule number 3, we will see that if we take the dot product of the unit vectors with themselves, we will have 1 as the answer, and we take dot product of unlike unit vectors, then we will have 0 as answer. So A dot B will be equal to ax bx plus ay by plus az bz. This was the rule number 3 for dot product. Now we will see that if we take dot product of A with itself, it will be equal to ax square plus ay square plus az square. The components will be squared, and if we want the magnitude of A in component form, and it will be equal to ax square plus ay square plus az square under the square root. Now we will see that if we take cross product of like vectors, like unit vectors, we will have 0 as the answer. But if we take unlike unit vectors for cross product, we will have z as the answer if we take x and y as for cross products. And we can have here negative z if we take left-handed system for the Cartesian coordinates. This is the component form of vectors. Now A cross B is taken as this form, as I have explained before in the cross product section. This is the rule number 4. If we take the cross product in this form, this will be very difficult. So we will take it in this form, determinant form. As you can see, firstly you will ignore this column and this row, and you will take product of ay and bz, as you can see here, and then negative sign, and then you will multiply az and by. Then you will put negative sign and j direction or y direction, and you will ignore this column and this row. Then you will multiply ax with bz, and then minus, and then you will multiply az and bx. Then you will put positive sign, and you will ignore this column and multiply ax with by, putting negative sign and then multiplying ay and bz. This form will you got. So this is the cross product of vectors component form. The third subtopic of vector algebra is triple products. We have scalar triple products and vector triple products. In scalar triple products, we will see that we have three vectors for which we have to take product, and the result or answer will be a scalar. So in the figure we can see that the product of B and C is taken, and this is the base of this parallelepiped, and we will take dot product of this B cross C with the horizontal component of this vector A, that is A cos theta, and this is the n unit vector of B cross C, and A dot B cross C is the volume of this parallelepiped. We can see that A dot B cross C and B dot C cross A and C dot A cross B are equal, but we have to keep the alphabetical order same. Now we can see that B cross A is not equal to minus A cross B, or A cross B is not equal to B cross A. A negative sign always comes. For non-alphabetical triple products, we have opposite sign, as I told you in the scalar vector product. Uh, if we reverse the position of vectors in this form, a negative sign will come before this matrix. So a negative sign will come here and here and here, because they are non-alphabetical. This is alphabetical, and it is the component form. The dot and cross can be interchanged, keeping the alphabetical order same. A dot B cross C is also equal to A cross B dot C. Now we will discuss vector triple product. In this, we will see that we have three vectors, and we will take their product, and the answer will be a vector. And they can be simplified by BAC minus CAB rule. As you can see here, we will firstly take dot product of first and last vector here, and the center one will come outside the bracket, and after minus sign we will take dot product of first two vectors, and the last one will come outside the bracket, either here or here. Now we can see that we can change the place of vectors by applying a negative sign, by assigning a negative sign, and same BAC minus CAB rule will be applied here also. And now we will see that if we have higher vector products, means if we have more than 3 vectors, we can also reduce them, but by applying previous rules as we applied in dot product, cross product, scalar triple product, and vector triple product. Same rules will be applied here. So taking the left hand side, we will interchange the cross into dot and dot into cross, and this will remain same. And now in the next step, this A will remain same, but we will apply BAC minus CAB rule here, and this will become B dot D C minus B dot C D. Now as you know that the answer of dot product is always a scalar, so we will consider it a scalar quantity, and this also a scalar quantity. So we will apply a rule here, that is, if we have a scalar with one vector, it can also come outside the bracket. So this B dot D will come outside the bracket, and A dot C will come here, and same here apply. So this is this topic. Now we have the subtopic position, displacement, and separation vectors. What is position vector? We will see here a point we have in 3 dimensions, and we can describe it in Cartesian coordinates x, y, and z. basically x cap, y cap and z cap, or I cap, j cap and k cap. So this is the point and these are the three dimensions, and this is the vector r which originates from this position or origin O, and its value is r equals to x cap plus y cap plus z cap, and we can also write it as x I cap plus y j cap plus z k cap. And if we take dot product of this r with itself, we will have x square plus y square plus z square, and this r dot r equals to r square. So if we take square root of this equation, we will have r equals to square root x square plus y square plus z square, which is the magnitude of this position vector, and this is the position of this vector or distance of this vector from this origin. So we can also have its unit vector, simply having the vector in numerator and its magnitude in denominator. This will be the unit vector, and it is radially outward from this region. So if we have infinitesimal displacement, or this vector space is infinite, then we have dl equals to dx x cap plus dy y cap plus dz z cap. We could also call it dr, but that will be confusing, so we write it as dl. Now we will see that in electrodynamics we have typically 2 points. One is source point, that is represented by r prime, and one is the point r where we want to calculate the electric field or magnetic field. As we can see here, this is r prime point and this is r. This is the source point, and this is the point where we want to calculate the electric field or magnetic field. So this is the separation or difference between these two vectors or vector points. So it will be represented by r, this type of r script letter, and it will be equal to r minus r prime, and its magnitude is taken in the mode. It means that magnitude cannot be negative or with negative sign, minus sign, and we will have its unit vector r vector over its magnitude, and this will be the unit vector. And if we write it in Cartesian coordinates, we will have x direction, y direction and z direction, and this will be the magnitude and this will be the unit vector. We have this vector in the numerator and this magnitude in the denominator. So this is the unit vector of position vector r. Thanks for watching. You can ask any question in the comment section, like the video and subscribe the channel for more videos.